Thank you all for coming to my defense presentation. I also want to thank all the professors for serving on my defense committee. Also, thank you everyone. So my thesis title is Threats and Opportunities of Mobile Sensing Technology in Personal Privacy and Public Security. So first, I would like to introduce myself. I'm a PhD candidate in computer engineering at Rutgers University. My research interests include cybersecurity and privacy, smart healthcare, mobile sensing and computing. I have published over 20 papers, including the top journals, top conferences, and the US patents. And I have received 3 Best Paper Awards from the top security conferences. And from 2014 to 2018, my studies have been reported by over 150 media outlets, including EBC News, BBC News, IEEE Spectral, and ISF Science 360. And the good news for me is that I have found a position, the faculty position, and I will be joining Louisiana State University, Baton Rouge, in this August. So today I would like to talk about mobile technology. So the mobile technology is a type of a category of technology that is related to mobility. With the mobile technology, what would you do? Good or evil? The earliest form of the mobile technology is a simple mobile device that you can utilize to send text messages and make phone calls. But nowadays, the mobile technology has evolved to multitasking devices, such as the smartwatches, smartphones, and IoT devices. They provide us with various applications. For example, the online banking, online shopping, internet banking, navigation, and fitness tracking. This is because they are embedded with powerful sensors such as touchscreen and motion sensors, also GPS and Wi-Fi. But while the mobile technology brings us with great convenience and flexibility, they also exposed many interfaces for the adversaries to attack us. And they could cause serious security threats and privacy concerns. For example, your account information, your personal PIN and password, your location privacy, and even your social relationships and demographics are all under a high risk to be disclosed. So in my thesis, I would like to study the security threats caused by the mobile technology. In particular, the personal privacy leakages from your smartphones and the personal sensitive information leaked from your smart wearable devices. Moreover, I would like to explore the opportunity brought by the mobile sensing technologies to do good things to us. For example, protect the public security by using the commodity Wi-Fi devices, or secure your personal privacy from the voice assistant systems, such as Google Home and Amazon Alexa, using the wearable devices. And today I will mainly introduce these 3 works. So the first major topic of my talk today is about the personal privacy leakage from the wearable devices. The work, Friend or Foe, Your Wearable Devices Review Your Personal PIN, has received the Best Paper Award from the ACM Asia CCS 2016 and was reported by over 60 media outlets. So as we know that the great convenience of the wearable devices has greatly stimulated the growth of the mobile market these years. And because of the increasing popularity of the wearable devices, they enable a wide range of useful applications. For example, the fitness tracking, falling detection for the elderly people, the gesture control, and the user authentications. This is because they are embedded with powerful motion sensors. But so the motion sensors can capture the user's motion and dynamics. But these embedded sensors may also raise a security concern that whether the user's privacy could be leaked. And in this work, we study and explore whether the user's personal privacy, such as the PIN numbers, could be leaked when the user is accessing the ATM machine, electronic door, or the keypad control server, all these kind of key-controlled devices. So the traditional attacks to the key-based security systems, for example, the ATM machines, mainly rely on the shoulder surfing, hidden camera, keypad overlay, and ATM skimmers. But all these methods require the direct visual contact to the key entry activities, which is hard to achieve in the practical attack. And they also require additional hardware and installations. So in this work, we exploit using the motion sensors on the wearable devices to capture the user's dynamics of the key entry activities. Based on that, we can recover the fine-grained hand movement trajectory and to review the user's pins. So the intuition is that when the user's hand movement between keys could cause unique accelerating and decelerating patterns that could be captured by the wearable's motion sensors. And here example, when the finger falls on the first key, the acceleration on the z-axis would decrease. And when the finger presses the key, the acceleration on the z-axis would increase because the inverse external force caused by the key. And when the finger releases the first key and moves to the next, there will be always the accelerating and decelerating pattern on the x and y axis. This is because the x-y plane is parallel to the keypad coordinate. And thus we extract these unique acceleration patterns to reconstruct the user's hand movements. But how can an adversary obtain such motion sensor data from the user's wearable device? We explore and find that the adversary could rely on two types of attacks to obtain such sensor data. So in the sniffing attack, an adversary could place a wireless sniffer close to the keypad and sniff or even stop the communication from the user's wearable device to the user's wearable device paired smartphone. And this sensor data could be obtained by the adversary. And in the internal attacks, an adversary could install the malware on the user's smartphone or even on the smartwatches. So the adversary could get the information and get the sensor data from the user's wearable devices surreptitiously without causing the user's notice. So there are a number of challenges we need to address in this work. First, to recover the PIN entries on the small size keypad, we need the fine-grained hand movement trajectories in centimeter level. And it is hard to obtain the labeled training data during the attack. So the proposed system should be training free. And it is hard to utilize the dictionary to infer the non-contextual PIN sequences. So our system should be contextual information free. And also the sensor data in the mobile device and the wearable devices are defined in the wearables coordinate. And we need to translate to the keypad's coordinate to recover the user's hand movements trajectory regarding to the keypad coordinate. So to address these challenges, we develop a system which takes the input of the motion sensor data. And then we perform the key-click detection and the trace segmentation to divide the motion sensor data into small segments, with each segment represent the data between every 2 consecutive key clicks. We then perform this calibration using the Quaternion-based coordinate alignment to translate the data from the wearable's coordinate to the keypad's coordinate, and also we remove the noises caused by the hand movement. Next, the fine-grained subpath recovery would estimate the distance and the direction of each segment data as the subpath. And then the backward PIN sequence inference algorithm will integrate all the subpaths together to recover the user's hand movement trajectory and utilize the tree-based PIN sequence inference algorithm to recover the user's PIN sequence. So as I said, the motion sensor data extracted from the wearable device is defined in the wearable's coordinate, but we need to translate it to the keypad's coordinate. So we developed the Quaternion-based method. So particularly, we first utilize the Quaternion extracted from the wearable device to translate the data to the word coordinate, which is a universal coordinate with x towards the east and y towards north. We then get the Quaternion that is obtained by the adversary regarding to the keypad. So we can utilize this Quaternion to further translate the sensor data from the word coordinate to the keypad's coordinate. And now we can utilize the translated motion sensor data to review to recover the user's hand movement trajectory. So given the motion sensor data for a PIN entry, we first segment them to multiple small chunks, with each small chunk representing the data between 2 consecutive key clicks. We then derive the subpath, including its distance and direction, to recover each subpath. And now we can integrate all these subpaths together to reconstruct the user's entire hand movement trajectory. To infer and estimate the distance of the subpath, we extract the unique acceleration patterns from the acceleration. And in particular, we search for the zero crossing point before and after the accelerating and decelerating patterns on the accelerometer data. And then we double integrating these accelerations within the starting and ending point using the trapezoidal rule to recover the distance. Besides estimating the distance, we also need to derive the direction of the subpath. So we define the angle to be the define the direction of the subpath to be the angle between the positive x-axis to the subpath, and the direction is derived by the ratio of the distance we estimated on y over the distance estimated in x-axis, and we also leverage the quadrant the user moves. So now we have recovered all the subpaths. So next thing is to integrate all of them together to recover the user's entire hand movement trajectory. But each subpath contains small errors during the distance and direction estimation. If naively integrated them together, the errors could accumulate to be very large and lead to the incorrect estimated results. In this case, the naively integrated path would lead to the result 529, but actually the ground truth is 419. To reduce the accumulated errors when we integrate all the subpaths, we developed the point-wise Euclidean distance accumulation method. Basically, we match the subpaths we recovered with the real K2K geometric vector to integrate all the subpaths together. And we calculate the Euclidean distance between the recovered hand movement trajectory with the real K2K distance. So here, we start from the enter key because we know that the last clicked key is usually the enter. And we run this algorithm in backward. So here is the example. When we want to test the possibility of the PIN candidate 846, we first match the subpath 3, and we move the ending point of this subpath to the key enter and calculate the Euclidean distance between the candidate K6 and its starting point. We accumulate this distance to D. We then match the subpath 2, and we move the ending point of the subpath 2 to K6 and calculate the distance between its ending point, its starting point to the candidate K4, and also we accumulate this distance to D. We redo this recursion, and the final accumulated distance describes the possibility of the matching this candidate to our recovered hand movement trajectory. So based on the point-wise Euclidean distance accumulation method, we develop a tree-based PIN inference algorithm to find the most possible PIN sequence with the minimum accumulated Euclidean distance as the estimation result. And note that because the ATM machine usually allows the user to enter the arrow pins multiple times, so we sort all these candidates PIN with the ascending Euclidean distance order, and then to start this best capability of the adversary to launch the multi-try attack. And to reduce the computation cost, we trim the tree node at each layer. So to evaluate our system, we recruit 20 volunteers and ask them to input the 4-digit PIN on 3 different kinds of keypad. We test 3 different wearable devices running under different sampling rates. So here is performance. And we find that our system can review the PIN entries from all the 3 different wearable devices on all the 3 different keypads with very high accuracy. in particular, the LG, with LG W150 and IMU, we can achieve over 80% accuracy with just the first try. And we also find that with a higher sampling rate, we can obtain the higher accuracy. And also, if we try more PIN candidates, we can obtain higher accuracy. And the right figure shows the number of tries the user need to, the adversary needs to break the user's PIN. And as we can see here, within 5 tries, an adversary could break over 95% PIN entries with LG W150 and IMU sensor. So to conclude this work, we demonstrate that we can utilize the wearable, wrist-worn wearable device to review the user's fine-grained hand movement trajectory. And we present a PIN sequence inference framework to recover the user's secret pins without requiring training or context information. And we develop a backward PIN sequence inference algorithm to infer the user's PIN entries accurately. And the extensive experiments show that our system can achieve very high accuracy within limited tries. So along this direction, I further studied the user's mobile payment privacy leakage from the user's wearable devices. The mobile payment has drawn considerable attention these years because it's a great convenience to make the payment over the mobile device anywhere at any time. For example, the in-store payment with Android Pay or Samsung Pay, or the in-app payment with WeChat Pay, and also the mobile money transfer. And the recent study shows that the passcodes, such as the pins and the patterns, are still the first choices of the most consumers to authorize the mobile payment. And in the previous work, we showed that the wearable could reveal the user's privacy. So in this work, we would like to study to what extent an adversary could recover the user's pins from the small size smartphone screen via the wearable device when there is no restrictions on their passcode inputting ways. For example, the user can hold the smartphone with one hand and wear the wearable with the other hand, the two-hand scenario. Or the user can hold the mobile device and the wearable device on the same single dominant hand, or even the single non-dominant hand. So we developed a system called the WristSpy to recover the user's passcode for various scenarios. For example, we developed the training-free methods to recover the user's passcode in the two-hand scenario. And for the single-hand scenario, we rely on the training-based method. But entering the passcode on the smartphone screen is very different from the key clicks on the physical ATM keypad. This is because the finger tappings on the smartphone screen keypad usually is much slighter and result in little acceleration changes on the z-axis. So to detect the slight finger taps on the smartphone screen, we developed the differential z-based click detection to magnify the immediate acceleration changes on the accelerations when the user's finger just hit the smartphone screen. And we can detect the click and we can recover the user's PIN entries. When the user uses the two-hand scenario and input the pins, we developed the parallel PIN decoding algorithm to decode the user's passcode. And because the mobile payment passcode do not have an enter key, so the algorithm needs to start from any possible keys in the first column and decode the PIN in parallel to reveal the user's pins. And we also developed the parallel pattern inference algorithm by taking into consideration of the unique pattern rules. For example, each dot in the 3x3 pattern grid can only be recorded once. This is a unique pattern rule. And also, if a movement from one dot to the other, if it passed the third dot, we need to check whether this point has been recorded before to add this to the pattern. And for the single-hand scenarios, because it's really hard to recover the hand movement trajectory from the motion sensors, So we resort to the machine learning techniques to study the hand vibrations resulted from the different finger press locations to review the user's PIN. So next, I would like to introduce our work to secure the public security using the commodity Wi-Fi devices towards in-baggage suspicious object detection using the commodity Wi-Fi. And this work received the Best Paper Award from the IEEE CNS 2018 and has been reported by over 50 media outlets. So in this work, we would like to study the public security threats caused by the portable dangerous objects, such as the lethal weapons, chemical explosives, and homemade bombs. These dangerous objects can be carried in baggage and taken to the public places very easily. And these years, these portable dangerous objects has caused many deaths and injuries. For example, the Boston Marathon bombing and the Florida high school shooting. After the school shooting, the Florida high school required their students to only wear the transparent bags. But do we really need these transparent bags, which show no respect to our students' privacy? Or the dedicated expensive hardware, such as the X-ray machine, which is so expensive and really hard to be deployed in the numerous public places, such as schools, museums, stadiums, and theme parks. So in this work, we propose to utilize the Wi-Fi signals to penetrate through the people's bags and determine the existence of suspicious objects. The intuition is that the dangerous objects, such as the lethal weapons, chemical explosives, and homemade bombs, are usually made of metal and liquid. They cause significant interferences to the wireless signals in the form of absorption, refraction, and reflection. In comparison, the non-dangerous objects and also the baggage, they are usually made up of fiber, paper, and plastics. They usually do allow the wireless signal to pass through easily. So such different impacts to the wireless signal indicates that maybe we can utilize the wireless signal to detect and identify the suspicious object hidden in baggage. So our solution is to utilize the wireless signal to determine, to identify both the material and the shape of the object hidden in baggage. We extract the fine-grained channel state information that is extracted from the Wi-Fi signals to capture the various wireless interferences caused by the object in the form of absorption, refraction, and reflection. The channel state information is a fine-grained description of the wireless channel in 56 subcarriers. And it also contains the amplitude and phase information, and it is a complex value. And our system consists of a pair of Wi-Fi devices with 2 to 3 external antennas, and it requires 2 separate setups to separately identify the material and the shape of the object. And the left setup is to place the object in between the transmitter and the receiver and close to the transmitting antenna. And this object could heavily affect the transmitting signals. By leveraging the signals passing through and bypass the object, we can identify the material of the object. And after identifying the material of the object, we further need to estimate its risk level. This is because a liquid object would have a higher risk if its volume exceeds a limit, and the metal piece would be more dangerous if its shape is similar to weapons. So we rely on the signal reflections extracted from the Wi-Fi signals to identify the dimension of the object, and the right setup magnifies the signal reflections caused by the object by placing the object away from the closely settled transmitter and the receiver. And our system, based on the low-cost Wi-Fi devices, can be easily integrated to the existing Wi-Fi infrastructure and deployed in the numerous public places such as school, museum, stadium, and theme parks. So our system takes the CSI, the channel state information as input, and we then adjust the psi phase to remove the unpredicted psi phase error, and we reconstruct the psi complex value to more correctly describe the wireless channel. Then the two-step material classification method first differentiated the dangerous object from the non-dangerous object based on the psi complex value. And we then derive the psi complex difference between receiving antennas to further identify the dangerous object to be liquid or metal. If the object is determined to be dangerous object, we further estimate its risk level. In particular, we extract the signal reflections caused by the object and estimate the shape for the metal object and the volume for the liquid object. So our system utilized the fine-grained channel state information. The psi measures the channel in 56 subcarriers. It is a complex value containing both amplitude and phase. But the raw psi data we extracted from the commodity Wi-Fi devices, they are corrupted by unpredicted phase error. As shown in this figure of the 5 subcarriers, we can see that it shows the donut shape. This is because the amplitude of the psi is constant, but the phase is more like random. We thus utilize the phase unwrapping and the linear transformation method to adjust the psi phase and reconstruct the psi complex value. And as the right figure shows that the psi complex value for all the 5 subcarriers are clustered for each subcarrier, and its amplitude and the phase keep constant if the wireless channel does not change. So with the reconstructed psi complex value, we perform the two-step method to identify the material of the object based on the capturing the signal absorption and the refraction caused by the material. And also we utilize a learning-based classifier to classify the material based on these wireless interferences. In step 1, we first differentiate the dangerous objects such as metal and liquid from the non-dangerous objects such as fiber, paper, and plastic based on the psi complex values. But we found that the psi complex, only relying on the psi complex alone, it is hard to further differentiate metal and liquid. So we derive the psi complex difference between the 2 receiving antennas to measure how the object scatters the signal to multiple receiving antennas. And we can observe that the psi complex value between receiving antennas, the psi complex difference between the receiving antennas can further differentiate liquid from metal. So after having identified the material of the object, we further estimate its risk level based on estimating its dimension. And we need to derive the reflection psi channel state information to capture the signal reflections from the Wi-Fi signals. And we define the reflection channel as the combination of 2 channels arriving at the same receiving antenna. We then perform the signal nulling techniques to let the 2 channels to cancel with each other by setting the weight vector, the weight beta. Based on that, we can remove the permanent reflections from the environment. And when there is a target object in the area of interest, we can capture the reflections caused by the object from the reflection channel. And the amplitude of the reflection psi reflects the object's reflection capability. So if the object is identified to be liquid, we further estimate its risk level by estimating its volume. We quantize the relationship between the liquid volume and the and the reflection psi amplitude based on linear regression and neural network-based method, and then we can estimate the volume of the liquid. And if the object is identified to be metal, we propose to estimate the dimension of the metal object. For example, it's a shape. And while moving the object in the area of interest, and we can find that we can get the contour of the metal box and the metal bottle when they are hidden in the baggage. And also when there are multiple objects hidden in the baggage. For example, the metal bottle covered by the clothes, the metal object would dominate the signal reflections and can still be classified and identified. So to evaluate our system, we utilize a pair of laptops with 4 external antennas. And they are running under the frequency 5 gigahertz frequency band. And we utilize 2 setups to separately identify the material and the shape of the object. And we test 15 target objects in 3 different categories and 6 representative bags and boxes. Here is the performance. Our system could achieve up to 99% accuracy to differentiate the dangerous object from the non-dangerous object. Moreover, our system can achieve up to 97% accuracy to further differentiate the dangerous object to be metal or liquid. For the object dimension estimation, our system can achieve 0.3 centimeters and 0.5 centimeters average error for estimating its width and height. And to estimate the volume of liquid, we can achieve a median error of 16 milliliters. To conclude this work, we utilize the Wi-Fi signals to detect the suspicious objects hidden in bag. And we propose 2 system setups to separately recognize the material and the shape of the object. And we adjust the psi phase to reconstruct the psi complex value. Based on that, we can measure the more correct channel state information. And we derive the signal reflections from the psi complex values. And based on that, we can estimate the shape of the metal object and the liquid of the liquid volume. And the extensive experiments show that our system can accurately detect dangerous objects in baggage, in various bags, and also estimate their shapes. So the last work I would like to introduce is to secure the voice assistant using the wearable devices. The wearable assisted low-effort authentication to voice assistants using the cross-domain speech similarity. And this work is under submission to ASAC 2019. So the voice assistant systems, such as the Google Home and Amazon Alexa, has brought quite a lot of convenience and flexibility to us. We can access these systems by simply speaking to it. For example, Alexa, turn on my TV, or hey Google, when is my meeting scheduled tomorrow? But these systems also stores the highly sensitive information of the users. For example, the shopping preference and the email contents, also the personal schedules, which could arouse the adversary's interest. And the adversary could simply access this information by simply ask, hey Google, what is in my shopping list? Or Alexa, read me my email. Or hey Google, list all the events in January 1st. And the study shows that the voice access is vulnerable to various acoustic attacks, such as the replay attack and the impersonation attacks. For example, an adversary could simply record and replay your voice to attack your voice assistant. But the existing defense method of the voice assistant system can only verify the weak word based on the audio features, and they leave the more sensitive voice commands unprotected from the attacks. And also, the authentication based on the audio features is not secure. The traditional method for the voice access systems is to verify the user's voice based on the voice features in the audio domain, such as the MFCC features and the spectral band centroids. But these methods only relying on the audio features has shown to be vulnerable to various acoustic attacks, such as the adversary could simply imitate or synthesize your voice to attack your system. More than the voice features, and many researchers propose to detect the liveness of the sound source to verify the voice commands. For example, they can detect the magnetic field from the electroacoustic transducers to detect whether the sound is from the machine speaker. And they can also derive the dynamic acoustic characteristics that are only related to the human speaker to identify whether the sound is from the human based on the time difference of arrival or the Doppler shifts. But these methods are designed for the smartphone. They require the user to place the smartphone close to mouth for the authentication, which is hard to be deployed to the voice assistant, which allows the user to speak from a distance. So in this work, we propose the wearable-assisted cross-domain user authentication to verify the user's voice commands by leveraging the wearable device as a security factor. The system is triggered by also simply triggered by the wake word of the user. And then the microphone of the voice assistant and the accelerometer on the user's wearable device will record the user's voice command and send the data to the voice assistant cloud service. And here we deploy our algorithm to perform the cross-domain similarity comparison. If the similarity is high, the system will accept this voice command. Otherwise, the system will reject the voice command and send a warning message to the user. And our proposed system can define the various acoustic attacks, such as impersonation attack, replay attack, hidden voice commands, and ultrasound attacks. And in addition, our system can be easily integrated to the existing voice assistant device and the user's wearable device without requiring the hardware modifications. So in our tag model, we consider an adversary who is interested in obtaining the user's private information from the voice assistant devices, which can be deployed in the office or at home, and they can be accessed by multiple users. And we summarize the potential attacks in two categories. When the user is absent from the voice assistant device, an adversary could launch the naive random attack by simply using his own voice to attack the user's voice assistant. And a more experienced adversary who has the knowledge of the user's voice could imitate and synthesize the user's voice command and attack the system. Moreover, an adversary who has the opportunity to observe the user's voice command could record and replay the user's voice command to attack the system. Even when the user is co-located with the voice assistant device, an adversary could still generate the hidden voice command, which is like a kind of acoustic noises that can be understood by the machine speaker, but is hard to be is incomprehensible to the human. And these hidden voice commands can be embedded to audio and video and played back through your laptop, your smartphone, radio, and TV, and cause serious security threats. Moreover, an adversary could modulate the voice command to the inaudible frequency band and utilize an ultrasound speaker to play back this attacking sound and attack the user's voice assistant surreptitiously. A question may be raised. So why do we use the wearable device to secure the voice assistant? This is because the number of the wearable device user has reached over 500 million in the worldwide, and it is natural for us to design a system to protect the huge number of wearable users without causing additional cost. Moreover, the wearable devices serve very well as the user ID for the wearable payment and the door access. So why do we use motion sensors, and why not a second microphone? This is because the accelerometer, the motion sensors, provide a distinct sensing modality to examine the signatures of the voice command in the vibration domain. But a second microphone is still in the audio domain, if an attacker could attack the first microphone, he can do the same to the second microphone. And the two microphone approaches has already been shown to be vulnerable to the hidden voice commands and ultrasound attacks. And second, a large portion of the wearable devices, they do not have a microphone, but most of the wearable devices, they are embedded with the motion sensors because their design purpose is to track the user's motion and dynamics. And the third, the low sampling rate motion sensors, they require low energy and low computation cost, which is favorable to the resource-constrained wearable devices. In comparison, using a microphone drains the battery fast. But how the vibration domain information different from the audio domain? We compare the frequency responses of the two sensing modalities, and under a frequency chirp signal from 0 hertz to 22 kHz, which is played back by an external loudspeaker. And we found that while the microphone can respond to the frequency, all these frequencies, the accelerometer can only respond to the low frequency range between 400 Hz to 3200 Hz. Moreover, the accelerometer's spectrogram shows the zigzag form, which indicates that the different audio spectrogram point, the different sound frequencies could generate the responses at the same low frequency point on the accelerometer. And because the human voice consists of many frequencies, which could cause the signal aliasing on the accelerometer. This is because the accelerometer does not contain a low-pass filter between the amplifier and the analog to digital converter. So the high-frequency sound is sampled by the low sampling rate accelerometer, which violates the Nyquist sampling theorem. And the signal aliasing can be expressed by this equation, where the F alias is the aliased acceleration signal's frequency, and F is the frequency of the original signal, and Fs is the sampling rate of the accelerometer. So this equation describes the relationship between the aliased accelerometer signal and the original acoustic signal. For example, sound frequency, 850 Hz frequency sound, when sampled by a 200 Hz sampling rate accelerometer, would result in a 50 Hz signal on the accelerometer. Here, n equals 4. Besides the signal aliasing, the accelerometer also shows the unique response characteristics in amplitude and frequency. This is because the mechanism of the accelerometer to capture sound rely on the subtle movements of its inertial mass, which is different from the microphone, which utilize the membrane to generate the capacity changes according to the acoustic signals. And we compare the microphone data and the accelerometer data under the same sampling rate for the voice command show facebook.com, and we can observe that both the frequency and amplitude of the two sensing modalities are different. And this is because the sensor structure of the accelerometer cause it to subdue some frequencies, while in favor of responding to other frequencies. And moreover, we find that the accelerometer has a very short response distance to the voice command sound. For example, 25 centimeters under the voice, the 70 dB voice command. All these unique characteristics make the accelerometer a good security factor to defend against the various acoustic attacks. There are a number of challenges we need to address in this paper. First, to match the voice commands across the two very different sensing modalities is very difficult. Moreover, they have a very huge sampling rate gap, which is, for example, the 200 Hz versus 44,000 Hz. And second, because the design purpose is not for capturing sound. The accelerometer shows low fidelity and low sensitivity to capturing the sound, and they provide insufficient acoustic information. And third, the synchronization of the voice assistant device and the wearable device is difficult, which could affect the performance of our system. And fourth, our proposed system should defend against the various acoustic attacks, no matter when the user is absent or present to the voice assistant device. To address these challenges, we developed a system to check the voice commands across 2 domains. Our system is initiated by the user's wake word, just as the normal use of the voice assistant device. And then the microphone on the voice assistant device and the accelerometer on the user's wearable device will record the user's voice command. And the 2 sensing domains data are closely synchronized and pre-processed for calibration. After that, the microphone data will be converted to the low frequency data that is comparable to the real accelerometer's data for comparison, based on the spectrogram-based frequency conversion. And after normalization, the converted microphone's spectrum will be compared with the real accelerometer's spectrogram to check the similarity to verify the user based on the shift 2D correlation calculation. So for pre-processing, we developed 2 alternative methods to initiate the authentication process and closely synchronize the 2 sensing modalities data. The Wi-Fi communication-based methods allow the voice assistant device, after receiving a wake word, to send out a message to start the data logging on the user's wearable device via the connected Wi-Fi network. And as an alternative method, the wearable device can also recognize the wake word by using the accelerometer in the vibration domain. That is in parallel with the voice assistant device. We also perform the noise removal to remove the hand movement noises and the mechanical noises from the wearables sensor data. And we also remove the high frequency acoustic noises from the microphone. We then extract the voice command segment from the data as shown in this figure. We can observe that the microphone data and the accelerometer data are closely synchronized, and we also show the accelerometer data before and after the noise removal. And we can see here the hand movement noise we affect the data, but we remove this noise. So our work is to check to do the cross-domain comparison to facilitate that. Our basic idea is to convert the high-frequency microphone data to the low-frequency that is comparable to the real accelerometer data. To achieve this, we resort to the time-frequency analysis and derive the spectrogram of the 2 sensing modality, the microphone and the accelerometer's data. Particularly, we calculate the discrete time, short time Fourier transform of the microphone and the accelerometer's data by using a sliding window. And the obtained spectrogram is a time series of the squared dt, st, ft. We then convert the microphone's spectrum to the low frequency spectrum that is comparable to the real accelerometer's spectrum. Particularly for each spectrogram point for the microphone, we calculate its the Pmac. We calculate its new position, Pmac dot, in the converted low frequency spectrogram, while the time point is not changed. And if multiple the microphone's multiple spectrogram points mapped to the same point in the low frequency spectrogram, we added them together, and the obtained new spectrogram point in the low frequency is calculated as Pmac hat. And here, the frequency conversion in the window function follows the signal aliasing equation as I introduced in the previous slides. But only converting the frequency is not enough. This is because the accelerometer responds to the acoustic signals with unique characteristics in frequency and amplitude. We thus analyzed the accelerometer's spectrogram and the converted low-frequency microphone's spectrogram under a frequency chirp signal. And we find that the accelerometer can respond to the small frequency range, the 700 Hz to 3200 Hz clearly. And only within this frequency range, we find that the acoustic responses of the two sensor modalities perfectly match. We also find that when the sound pressure level is over 70 dB, it can leave the obvious readings on the accelerometer. So we convert the microphone's spectrogram following the unique amplitude and frequency characteristics. We thus developed the spectrogram-based conversion algorithm by integrating the spectrogram-based frequency conversion with frequency selection and amplitude selection. The resulted low-frequency microphone data is now comparable to the real accelerometer data. So we now, we can compare the voice command across two domains. We first performed the role-based 2D interpolation to align the two spectrograms in the time axis. We then performed the column-based 2D normalization to normalize the magnitudes of the spectrograms of the two sensing modalities. We then checked their similarity across domain by calculating the 2D correlation coefficient. And A and B here represent the metrics of the spectrogram. In order to further reduce the synchronization error between the two sensor modalities, we performed the shift 2D correlation coefficient calculation, and we find the maximum 2D correlation coefficient as the similarity score of the two domains. And here we show that the similarity score for 20 voice commands when we cross-comparing them, and we see that we can differentiate clearly. Here we evaluate our system with two smartwatches and one voice assistant, and we recruit 20 volunteers, 10 volunteers to speak 20 voice commands. And we evaluate our system with a true positive and false positive rate. And the results show here that for the normal situation without attack, our system can show up to 99% accurate true positive when the false positive is 0. And for the random attack and the replay attack, we achieve up to 98% and 90% true positive rate when the false positive rate is 5%. And for defending the hidden voice command, for the Huawei watch, we can show 100% true positive rate. And for the LG watch, we can show the 95% true positive rate, while the false positive rate is 0. And for the ultrasound attack, we show that the two watches do not respond to the ultrasound attack from the 15K to 25K Hertz, while the microphone can still be attacked. So for the conclusion, we show that the motion sensors of the wearable can exhibit unique responses to voice commands in the vibration domain, and we identify the complex relationship between the two sensor modalities to facilitate the cross-domain comparison. And we present a wearable-assisted verification system for the voice assistant. And the extensive experiment shows that our system can verify the user accurately under various acoustic attacks. So these are the papers related to during my PhD study, and that's the end of my talk. And I would like to, finally, I would like to thank my advisor, Professor Chen. Thank you very much for giving me the golden opportunity to research in cybersecurity and privacy, also mobile computing. You really helped me a lot. I can never forget the many times we fight together for the paper deadline. And you also give me many guidance to be a good student, also to be a good person. Really thank you very much. And also, I got a faculty position. It's really hard in the competitive job hunting market. And I'm really glad that I'm a student of your group. And also want to thank you for all the professors for being my defense committee, and also all the students for coming today. Thank you very much. And I'm happy to take the questions.